This is very important to keep this in mind, otherwise you cannot understand the phenomena. And here it is shown what's happening. I cut potatoes. Potatoes are very good to use and to show microwave influences or radio frequency influences on a product. Why? Because a typical potato contains two important enzymes, peroxidase and phenol oxidase. Both are not stable in heat. If you use heat, you can inhibit these enzymes, and both enzymes, peroxidase and phenol oxidase, are the reason for browning of potatoes when you cut them and store them in ambient air. You know this. You have to boil potatoes, otherwise they will lose their color. And in this case, we use this system to show how the microwave penetrates into potatoes, and to accelerate this browning and to intensify this browning, we took guaiacol alcohol. We put these potato cubes in guaiacol alcohol, and guaiacol alcohol is a catalyst which is improving and intensifying this browning reaction. And when you see the borderline between those yellow parts of the potato and the brown parts, you can see the temperature zones, different temperature zones. In this case, we have not exceeded temperatures of 60 degrees, and here we have done it, because under 60 degrees we are not able to inhibit phenol oxidase or peroxidase, and in this case we did. And you see, we get a sharp borderline between those areas. And what can we see here? Now, I put a 1000 watts of microwave power with a technical trick only from one side of the product into the potato. This is a photo made after 100 seconds, after 200, 300 seconds of application, 400 seconds and 500 seconds of application. And what you can see here is that really the penetration depth is small. This is really only 1 centimeter or something like this. And after 200 seconds, we got a little bit more into the product. Why? Because now water is evaporating and the water content goes down. And with the loss of water, we get a higher penetration depth, because the microwave is not attenuated here in this area, and so we get a propagation of the temperature zone up to perhaps 400 seconds with quite similar propagation over the time. But you see that when we reach 400 seconds up to 500 seconds, we have no change in it. No change in the front, only a small change. Why? At this time, in the surface here, upstairs, in the top part of the potato, we have temperatures of 100 degrees centigrade, and we have a fast evaporating and drying process. You can see that the material is shrinking, and that an effective drying is happening, working here in this area, and therefore lots of the energy is consumed here by water vaporing or producing water vapor. And due to this, we got no energy into the deeper parts of the potato, and at this time we have only a heat transfer by conduction and not by direct microwave influence. So you will not be able to dry materials as thick like this one with homogeneous drying process when you use microwave energy. And to overcome these problems, we changed in this case to radio frequency. And now we are going away from the product, we are coming to the hardware, to the equipment. Here you see two systems. This is the microwave application system, and this is the radio frequency application system. Here we have lower frequencies and higher wavelengths of several meters, and here we have higher frequencies and lower wavelengths. This is the typical microwave oven, as you know it perhaps from your home or from your kitchen or whatever you have. The energy is brought into the system with an antenna, same with a mobile phone. every mobile phone has an antenna. Sometimes you cannot see this antenna, but it is inside, and it is sending electromagnetic energy out, broadcasting out into the atmosphere. In this case, not into the atmosphere. This is sent into what we call to a special coupler, a so-called waveguide. This waveguide brings the energy into the system with, in this kind, not in the kind of, in the manner and in the field of a household microwave oven, with defined wave structure. There are different wave structures possible, but in this case we get a defined wave structure. This energy and this wave is now running through the system and is reflected on the metal surfaces, and in this way, after several reflections or directly, it is attenuated in the product from different sides. So we get another thing like here we get only the energy from the top, but in the typical household microwave we get it from every side. So you can overcome these problems of inhomogeneous field distribution. But you get really, also in a microwave oven, you get an inhomogeneous field distribution. The ingoing and reflecting waves sometimes meet them, and then you have so-called hotspots. Here, for example, you have lots of energy, and there is a net of different knots in this system. I have only shown this one here, for example, to make it clear. Here you have a high energy concentration, and perhaps beside this area here, for example, you have no energy. And this is the reason why you have to move the product in the system. You cannot leave it without moving, otherwise some parts of the material will only stand in a knot and other parts will stand between. And you can also change this by using a special propeller, which we call steering propeller, which changes the inhomogeneous field distribution. But this is a problem in microwave transportation, which you do not have in the case of RF application. Here you have a very homogeneous field distribution, and therefore it is more interesting sometimes for industrial purposes to work with this one than with this one. In the household, you will perhaps use microwaves for heating up something, and this is not a problem because you have water in it, and if you have water you get heat conduction in the system by conduction and also by other heat transportation mechanisms. But if you want to dry material, you don't have this opportunity, and then you have to have a careful look on the field distribution, but not in a normal household microwave oven. And on the other hand, in industrial applications, we need higher penetration depths of several meters. For example, if you want to clean or dry a big bag of rice, you cannot do this by microwave because they are not able to enter this big bag of rice. They will not come into the middle of the system. Here, in the case of radio frequency, it is easy because we have wavelengths of up to 11 meters. You can use the whole room here for applying radio frequency, for example. This is quite easy, and radio frequency is easy because you have only two systems. One capacitor plate at the top with positive and at the bottom with negative loading, and then you change the loading between the condensator, the capacitor plates, and everything is working quite easily. So here you see the microwave system. The microwaves are produced on a so-called magnetron, and here you have the coupling instrument, which gives a defined wavelength, and here you have the wave stirrer or something like this, and then you put the microwave energy into the system, and you can heat up and boil your chicken or whatever you want to do. This is typical normal household. This is an RF applicator. The system is quite similar. We have an application chamber. In the chamber we have the upper and the lower electrode or the capacitors, and in between these capacitor plates we have the material. And you can lower and raise this capacitator plate because you must bring the product in direct contact with the capacitator plate. Air is something like is hindering and the magnetic wave to propagate into the material. The rest is only of scientific interest. With these things we can control the energy which is sent in the product, and we can perhaps discriminate the kind of wave which is produced, but it is not of common interest today. This is the system. And now we want to look on the fields of application. One field of application, and this is typical, is drying. We have effective drying methods, but the convection drying process is restricted through different things. Air velocity, temperature, you cannot raise the temperature in a typical convection drying process without having influence on the product quality. On the other hand, you cannot accelerate the air velocity because high air velocities cause huge demand for electrical energy, and this is very expensive. And there is one problem that might occur in future when you use air for drying purposes, because especially with respect to consumer protection, you have to use clean air for this purpose. You cannot use ambient air for drying. Perhaps you do so, but if you, for example, dry foods, and according to EU regulations, food is also produced in the field. A farmer in the European Union does not produce any kind of agricultural raw materials. He is producing fruit from the beginning of the harvest. This is the interpretation of the European Union, and therefore the farmer is not allowed to apply, for example, ambient air. He is allowed to do so because ambient air can be used for drying purposes, but I'm not sure whether this will be right in future, because ambient air can also be exhaust air, contaminated with small particles from traffic, from other industrial processes and so on. If you have to clean the air, it is a hard job to do so. And then we need other drying techniques, and perhaps one of these technologies might be not microwave, but I think radio frequency. Another field of application is the sanitization of food and feed. I will give you some examples on this. Eradication of seed-borne fungi in seeds. This is a special field. We are working together with the Post-Harvest Technology Institute here in Germany. Pest control, for example, insects in crops, also a field of research we do together with Germany. And last but not least, conditioning and processing of plant materials. And I mentioned before that we are also using radio frequency for traceability of agricultural products. So there might be other fields of application in future. Here you see a typical microwave drying experiment. In the case of majoram, which is a spice which is used in the German meat industry, and this is one of the very seldom spices that can be grown in Germany. Most of them we are importing from other countries of the world. I don't think many of them also from Thailand. But in this case we have our own sauce, and here you see a typical drying experiment with convection drying, here with a temperature of 40 degrees centigrade, and here with higher temperature, 50 degrees centigrade, and here with microwave energy. In all these cases we used, we measured the mass flow and the mass decreasing over the time, and you see in the case of convection drying with 40 degrees centigrade, it took more than 6 hours to get dry material. Then we changed the temperature up to 50 degrees, a typical behavior which you do in the drying technology, and you see we shortened the drying time and we reduced the drying time to about 4 hours. But with certain quality and quantity. This is the etheric oil content. We have here, after this time we had 1.8%, we have 1.9%. And then we use controlled microwave. This, for microwave drying process, this is very long, it was 2.5 hours, but we reduced the temperature only to 40 degrees centigrade. The temperature was not exceeded and did not exceed 40 degrees centigrade. It was comparable to this green curve, but you see it was very much more effective than the convection drying, and it was better for the quality. The oil content was about 2% after 2.5 hours with 40 degrees centigrade. And perhaps you might ask, why does this happen? Because you in both cases we use the same temperature. I will come to the explanation later. It's quite an easy explanation, but when you look into the product, but we have to do this later. When you use microwave, you can also accelerate the drying process to up to a few seconds. For example, we made drying experiments with medicinal plants like digitalis leaves, for example. In this case, we took less than 10 seconds to make a fresh product to a dried product. But this is a very special case, and I will not look for it. But here you can see the effect of microwave drying, especially also in this case of medicinal plants. This is Viola tricolor. These plants were grown in Austria, and they were dried by microwave in this case, and this is air-dried, convection-dried material. And you see the difference. There's a clear difference. I think this looks like similar to the fresh product after microwave drying. And the explanation why this product looks very much better than this one is quite easy. The time of drying is so fast that, and the water is removed so fast that no chemical reaction in the direction of the deterioration of the product can happen. We have a very fast drying process. The water is blown out of the material, and there is no time for changing the color, for deterioration, the quality, or something like this. This is a very good example how microwave can work. This is sometimes also a market problem, because some of these retailers who sell those materials say we cannot sell this because the market does not know that that a product like this can be produced. You know that medicinal plants are handled just by optical impressions, and a product like this is not on the market, and therefore you cannot sell it. This is the problem. The quality is excellent, but nobody is accustomed to it, and therefore the market refuses to take this product because they say this looks like a little bit artificial or made of coming out of a chemical company or something like this, and this is a problem. Here you see the Myoram, convection dried and microwave dried, and even in this case you find better quality. Microwave dried material, we measured this with, I can maintain that this is better quality, but we have an optical measurement system where we can measure this, and we found out that the microwave product looks better than this one from the convection drying process. And here an attempt to explain what's happening during the microwave drying in such a product. Here we have two potato slices. The left one is a slice and the right one is a slice, and they are cut, and we looked inside, and to get an impression of the structure of the material, we colored the structure with Congo red. This is a special color which is able to show what's going on in the system. You can see a typical phenomenon from the convection drying process of potatoes. You see that we get a hard surface of starch, which is hardening the surface of the potatoes and burn and threshold for evaporating water. How does this come? The reason is easy. You have in a fresh potato which you cut in slices, you have a solution of starch in the water, and with the water, when the water is evaporating through the surface, with the water you have this soluted starch, and it is wandering to the surface. And at the surface, the water is evaporated and the starch is concentrated, and it makes a close layer over the potato, and then you cannot dry it very effectively. In the case of microwave and also radio frequency, remember what I explained to you. The energy is set free by friction between the rotating molecules. So the water is closed in the intercellular and the cells in the potato. It is directly heated, and you get a huge increase in temperature. And when you reach a temperature of 90 or 70, 80, 90 degrees centigrade, you get water vapor. And this water vapor causes a huge force inside the material, and it, let me say, the material explodes in some way. It explodes and you get big cavities. And big cavities from big cavities you can remove the water very easily, and this is an explanation. This happens in nearly every product except those products where you get no influence on the surface, but this is not a matter we have to discuss today. You get an impression what happens in the product. You get a totally other design of the texture of the potato after dried in the microwave system, and therefore you get these high drying velocity.